In this video, we will conclude receiver diversity. But first, we will look at the example of performance improvement in case of MRC. So let us consider we have three antennas. We have three antennas, 1, 2, and 3. So we have one is the stronger one, and the two are the weak antennas providing an SNR of 5 dB each, and the stronger one has an SNR of 15 dB. So the first case is compute the probability of error when you have only one antenna, that is the stronger one, that means 15 dB. So you substitute this value of gamma 1 bar into this expression. You have only one antenna and you will get probability of error to be equal to 0.015. Now second case is consider all the antennas. You consider the strong antenna, but now you also consider the weak antennas. And then you substitute this gamma values into this expression, probability of error. You will get probability of error is equal to 8.9 into 10 raised to power minus 4. So from here, you can see that you have an improvement even when you combine your signal with the weak antennas. So this is the importance of MRC. So even if you combine weak antennas, you still get a less probability of error. So in general, we have this expression gamma MRC is always greater than or equal to gamma EGC is greater than gamma selection combining. And this gamma MRC can be equal to gamma EGC, and this is the case if you have equal noise variances in every branch. Then in that case, gamma MRC is equal to gamma EGC because you are only doing co-phasing and you are not taking into account the noise variances because the noise variances is same for all the branches. So then if you look at the SNRs for each of the expression for MRC, SC, and EGC, you will find out that, and this we have studied, that in case of MRC, when for all the branches, if gamma is same, then you can write it in form M times gamma bar, and the SNR increases linearly with number of antennas. In selection combining, we have discussed about this form. And then in case of EGC, when we have M number of antennas, then we use this M minus 1 in between multiplied with pi by 4. So what is happening is that the BER, the probability of error, it depends on the type of diversity. Why? Because this probability of error depends on the PDF. Here in between, it is the PDF of the SNR, and the PDF of SNR is different for different combining schemes, because this combining schemes, they change the statistics of the SNR. So whenever you change the statistics of the SNR, that means whenever you change the PDF, so PDF is increased. So when you go from selection combining to EGC to MRC, probability of error is decreased, and so you have probability of outage probability is also decreased. And this diversity is beneficial in case of fading because of the diversity, what you are getting is basically, let's say this is the BER plot, SNR in dB, and this is log BER log x's. So this is M is equal to 1 for fading. So whenever you have fading, you increase the number of antenna elements. Basically, you are changing the slope of the bit error rate plot. So that means the probability of error is decreasing. So this is beneficial in case of fading. So what if there is no fading? Does we have diversity in AWGN channel? So let us see. So in AWGN channel, we have Y1 plus Y2, 2 times X plus N1 plus N2, and we have 4 ES by 2 sigma N square. This 2 will get cancelled and you will have twice ES by sigma N square. So that means you get twice the SNR. Twice the SNR implies you are getting a 3 dB benefit. So that means if you do not have fading, if you have AWGN channel, in case of AWGN channel, the diversity is giving you 3 dB benefit. And this is the constant benefit, and this benefit is known as the array gains. So what it implies is that this is a constant. So let's say if you have m is equal to 1. So this constant shift will give you, this array gain will give you a constant shift of 3 dB. Okay. And it occurs for all the diversity techniques, and it gives a constant shift in the BER plot. And the array gain is defined by the ratio of the average SNR achieved through diversity to the average SNR of single antenna. Let us consider, for example, when you have MRC. In case of MRC, you have M times gamma bar divided by gamma bar. So this will get cancelled out. It will be equal to M. So the array gain is maximum for MRC, which is equal to M. And this is often called as beamforming gain. And this is the first advantage when you have multiple antennas. Why? Because when you have multiple antennas, let's say you have 3 antennas, you can change the phases of each of the antenna elements appropriately such that it should form a beam in a particular direction. So whenever you are forming a beam by adjusting the phase corresponding to each of the antenna element, this form of gain is known as the beamforming gain. Okay. So then you have diversity gain. So in the absence of fading, you have array gain. When you have fading, you have diversity gain. And when there is no fading, diversity gain is basically array gain. So there is no diversity gain. You have a constant shift in the BER plot that is described by the array gain. So diversity gain is because of the reason that when you combine antenna signals, it changes the SNR, it changes the statistics of the SNR, and the changing the statistics of the SNR means reducing the probability of error, and reducing the probability of error, you are reducing the outage probability, and thus you have improvement in bit error rate. And if there is no fading, then there is no need for diversity because you will only get array gain. And in case of diversity, the probability of error is defined by this particular expression where we have C constant and multiplied by 1 by gamma bar raised to the power L, where L is the diversity order. This is less than or equal to M. And this diversity order L gives us the slope of the graph. And if this L is equal to M, then we say that we have full diversity performance. And if L is less than M, then we have less diversity performance. And why we have L less than M? Because in some cases we may have correlated antennas, or maybe you have not utilized the optimal combining, or there are some implementation losses. Then in that case, L is less than M. So what it implies is that the array gain and diversity gain, what it implies is, let's say you have this BER plot. This is in log axis, and you have SNR in dB. So first you have, let me change the pen. This is for M is equal to 1 fading scenario. Now when you add additional antenna, so you will get 3 dB benefits. That means you are getting a constant shift in the BER plot. So that means you are getting a constant shift here. And this particular shift is because of the array gain. And this is for when M is equal to 2. So this is the minimum that you can get when you have M is equal to 2, that is array gain. the more you can get is from the diversity gain that changes the slope of the graph. So when you have diversity gain, it changes the slope. So this is what you are getting from the diversity gain. And in total, this one is as a result of diversity plus array gain. And whenever you increase the number of antenna, this curve goes to the left. And basically, you are decreasing the probability of error. Now, what will happen if everything is same? The fading environment is same, statistics of the SNR at both the antennas are same, or if both the antennas, they are correlated to itself. For example, if you have signal to antenna 1 in this fashion, and then you have signal to antenna 2 again similar to this one, then what you will do? You have two antennas. Should you throw away the second antenna because there is no helpful in the second antenna? Or let's say there is no fading, all the antennas are correlated. So then in that case, should you throw out this second antenna and only focus on the first antenna? No. Why? Because addition of the antennas give me a 3 dB benefit, that is array gain. So thus, whenever we add a new antenna, you get a constant shift in BER from the array gain. So even if everything is same, even if it is AWGN channel, still you will get a constant gain, that is array gain. And from more you can get from the diversity gain. So with this, we have completed our discussion on the receiver diversity. We have first covered selection combining. Thereafter, we looked at the cophasing. And then in the last, we discussed about optimal combining. And then we discussed what is array gain and what is diversity gain.